Hi, and this is the Physics High podcast. A quick quiz. Do you A, want to be inspired by science communicators? B, want to learn all about science education? C, want guidance on your scientific journey? Well, how about D, all of the above? So when you think of solar cells, you're thinking those glass panels that you'll find on roofs everywhere and also in solar farm fields. But you certainly aren't thinking of materials that are flexible and bendable. Imagine if we have solar cells that you can literally spray on surfaces, whether it's on windows or plastics and so forth, and to be able to transform your house into one giant solar panel. Well, today my guest is Dr. Anita Ho-Bailie, who is the John Hooke Chair of Nanoscience at the University of Sydney, and she is an internationally renowned expert in the study and development of perovskites, which is a type of material which can be modified to become solar cells. And imagine to use that material to spray on substances and thus become a source of electricity. Welcome, Anita.
Thank you, Paul. Thanks for having me.
Now, you are the John Hooke Chair of Nanoscience at the University of Sydney. Just in case some people don't know, what is nanoscience?
Nanoscience is science to do with things that are very small in nanoscale. So what's nano? Nano is as close to as you can get to the atomic level. Piece of hair is around 75 microns, which is huge. So if you divide it by 1,000 times, you get to 7.5 nanometers. So it is 1,000 times thinner than than the hair, human hair, for example.
So in your area that you're the chair of nanoscience, what sort of work is happening in that module at the University of Sydney?
Right. So lots of things happening. There's quantum computing activities happening. As you get to that scale, a lot of classical physics don't apply, and you have quantum physics happening, and you have, for example, we're using like quantum interference for interfacing solar cells. And also as the size of materials gets smaller, you may be able to engineer properties that you would not normally get using classical physics.
Now, going specifically into your area of research, really is about the perovskites that you are working with. Your work really is about making solar cells, solar panels that are hugely more efficient than the current technology based on silicon. Can you tell us a little bit about your work?
Yeah, so our work is to advance solar technology. So we want to make them more efficient, and we want to open up new application opportunities of solar. So, my dream is to cover every service with solar. So my background is actually silicon. So I started off, working on silicon for my PhD and my postdoc. And then in 2013, there are a few publications out there reporting this material called metal halide perovskites, which is a class material that's just got the crystalline structure that resembles like calcium titanium oxide, which has been found ages ago. Anyway, this metal halide perovskite, this cells made of metal halide perovskites are 10% efficient, which is quite phenomenal when you're looking at it as new materials. And then the multiple groups reporting that. And then I started following the publications in the area because we thought maybe we can stack it on top of silicon to form a tandem cell. And I can touch on what tandem cell means. So I remember in 2013, there were 83 papers reporting this metal halide perovskite, and I read every single one. And in 2014, there were 200, and I just couldn't keep track of reading every single one. And what attracted me was you can make perovskite solar cells really easily. In the silicon technology, what you do is you purify silicon from quartzite, which is a purified form of sand, which is essentially silicon dioxide. So you purify it to metallurgical silicon. And after that, you purify it to polysilicon. So you bring the purity level from 98% to 99.9999%. And then you grow the silicon into a single crystalline form so that you will get the optoelectronic properties that you want. and then you slice it, and it goes through another few 1000 degree temperature processes to make it into a PN junction, and then becomes a solar cell eventually. But with perovskites, you dealing with the perovskite precursors, which is a metal halide, for example, lead iodide or tin iodide, or lead bromide or tin bromide. And then you mix it with another salt, which is also a halide, but it could be an organic halide. You dissolve it into a solvent and you deposit it onto a piece of a substrate, whatever that carries that solar cell, gives it 100 degrees to 200 degrees Celsius, not 1000. And within, a few minutes, it self-assembles and it forms this crystalline film that is photoactive, that is a solar cell. That was really amazing when I look at that. You can actually make a solar cell like that. And it still amazes me when I see the students do that in the lab. The color changes to a black color film, meaning that it's absorbing all the light that it sees. And it's eventually going to be a solar cell, within a few hours later, you finish it off, there will be a solar cell. Take it out to the sun and it can turn a fan, connect it to a fan. So that just create a lot of following, both academically and also, their money being poured in, looking at commercializing the technology.
In many respects, the silicon-based is the amount of energy that's required to liberate the electrons is very specific, referred to, of course, as the band gap. And the beauty of my understanding of the perovskites is that you can tweak and modify the band gap in the process. And then, if I'm correct too, you can then also layer different band gaps so that you can capture more energy levels, so to speak, to therefore convert into electrical current as a result. Tell me about what the challenges is in producing something like that.
Okay, well, one of the challenges, so you can change the composition. So by changing the halide composition, so it's really the halide that is responsible for for determining the band gap of the material. So iodide would give you a smaller band gap, and the bromide will give you a larger band gap. So if you want to do anything in between, you actually mix the two together, iodide and bromine. But at times, the bromide or the halide or the iodide tends to segregate. So you can have a situation where one of the halide wants to go to so the film is multicrystalline. So there will be areas where it's not quite crystalline, it's sort of like very amorphous, and we call it the grain boundaries, where the grains meet. And they tend to go to those areas. So we call it halide segregation. And then it mucked up your band gap. So even though you want to tune it to maybe, say, 1.7, at times, given the right energy, thermodynamically, you will have the halide want to go to certain places in the film and doesn't do exactly what you want. But there are recent studies that if you put in additives or you deliberately engineer the conditions that the solar cell in, for example, if you give it a bit of light, the halide will segregate. But if you give it lots of light, the halide actually won't segregate. And I may not go into the details of that, but you can engineer it so that you use the cell as a concentrator cell. So you use optical elements to deliberately concentrate more sunlight onto the cell and to sort of just, annihilate that halide segregation effect. Anyway, the halide segregation effect, people at the School of Chemistry in Sydney Uni and also in Monash, they had a joint study. They reckon it has something to do with the crystal being in a strain position when they see light. But if they see a lot of light, that strain is evenly spread across the film, and therefore you don't have that gradient that the halides want to go to somewhere, bromide iodide want to go somewhere, and bromide wants to go the opposite direction.
Silicon had a doubling of efficiency over 40 years, and you've had a doubling of efficiency over, 4 years or something to that effect? A much shorter...
10 years.
10 years. So, why aren't we using this now?
So one of the one of the holy grail of perovskite cell is their stability and durability. So they're easy to form, but they can be easily decomposed if you're not careful. So perovskite cells that are not protected, they will just die when they see moisture and when they experience heat. So what we found is, well, moisture is easy because you can protect the cells from moisture ingress. But what do you do with heat? So what we did was we studied the cells when they're thermally stressed and see what happens. And we found that the organic component of the perovskite actually outgas. So they just come out of the material. And we found that if we stop that outgassing, we deliberately cover it, literally physically covering it, and not create an environment for the outgas to come out, we can actually stop the decomposition reaction. And so we found that the material or the method that we use to protect the cells from moisture from going in, we can actually use that same method to stop the outgassing from coming out. So it was like one thing that, one stone killed two birds, I think. And yeah, so we're able to protect the cells. The cells early on 10 years ago, they last for, a few days when they were reported in the literature. And now we're able to stabilize it so that it will pass the, three major industry standard tests, which is the thermal cycling, dam heat, and humidity freeze. What we did is you don't have a lot of years to hang around and then look at the cell to see if it, if it's stable. What we did was accelerate test them. So we torture them through thermal extremes, for example, minus 40 to 85 degrees. We just torture them and recycle them up and down. We torture them for like 200 cycles, 500 cycles. Also, we expose them to high humidity, 85 degrees, 85 relative humidity, 85% and 85 degrees Celsius for a long time, for 1,000 hours. We also thermal cycle them, and then we drop the temperature so that if there's any ice crystals that seeped into the cell, then they will, if we have any leakage, it will break the cell apart through the ice crystals. And found out our encapsulation is doing really well, and our cells are able to exceed the requirements of those ISE standard industries tests.
A more difficult question and requires a little bit of a crystal ball, but clearly the technology is not ready to be commercial as yet. Do you see 4, 5, 10, 15 years to a level that we're going to have commercial applications?
Well, I'm optimistic because we're working with industry partners. So our job is to, get those technological advances to make sure we can increase the performance, we can make them durable. But then we do rely on the industry partner to commercialize it, and they are the pipeline between us and and putting it out in the real world. So yeah, I'm very optimistic actually, and there are quite a lot of startups that popped up. Some of them are started by PhD students, and some of them are started by professors. So yeah, so I'm very optimistic, and I guess the tandem technology is quite promising, where you can stack a higher bandgap material on top of lower bandgap material, where the lower bandgap will absorb the red part of the sunlight really well, and the high bandgap material will absorb the bluer part of the sunlight really well. And when they work in tandem, they absorb the sunlight much more efficiently and therefore give you a much higher energy conversion efficiency. Whereas with a single junction solar cell, what happens is they absorb sunlight that is close to the bandgap really well, but with sunlight with photon energy that is quite high, it can actually get wasted by the solar cell. So that excess energy turns into heat. It doesn't make your solar cell hot. So, we call it thermalization loss. So by stacking cells on top of each other, we get that, boost in efficiency. For example, for single junction, 30% is the theoretical limit. When you get to 2 junctions, it's 40%, and when you get to 3 junctions, 50%. So Yeah, so that's a quite a promising technology.
And I would imagine it's a deliberate pun, you're in the right climate in terms of the fact that now with a growing push for renewable technologies because of climate change, that you're getting good funding now for your work as a result.
Yeah, so we're funded by the Australian Research Council as well as the Australian Renewable Energy Agency, which has been a great supporter of our work. And I think it started around 2007, around that time. And it's been going, there have been talks about, whether, ARENA, Australian Renewable Agency, will be renewed. And so far, it's been renewed. And yeah, we just hope that we're able to do good work. And I think in the last 10 years, because of ARENA, we're able to not just advance the technology, but build a community, build a scientific community. I think through the program, through the few research centers that are funded by ARENA, I was able to meet a lot of researchers that I never knew before across the states. And yeah, we have formed a very good partnership as a result.
Moving on now to, I guess, a little bit more closer to home. What got you into science? Were you the type of person who's always loved science, or was there some sort of seminal moment in your primary or high school career that switched you on?
I always liked maths and science at school, and I did do well in maths. And I didn't know I was good at maths until I was in high school. So someone made a comment and say, wow, you're pretty switch on when it comes to, just getting the concepts right. So I thought, oh, okay, well, that's good. So I did well in maths and science. At high school, I did well in my HSC. And there were different pathways and, I could have done medicine, but then I thought, I'm not so sure about the sight of blood. And I thought about doing vet science, but then I read James Herriot's book. And I think the first chapter was about carving. And I just thought, oh, there's no way I can, fight off that big beast. And, vet science is not always about small animals. So, yeah, so I went into engineering, went into electrical engineering. And I remember the first day, back in the old days, we had to line up in person to get ourselves enrolled. And I enrolled to advanced maths. It was funny. The guy said to me, are you sure? He looked at me, he looked at my face, he looked at who I am, and he already made up his mind that I'm not good enough. I showed him my HSC results and he was a bit embarrassed. He went really red and he signed it and go, yeah, next. Anyway, so how did I get interested in solar? Well, in my second year in the electronics course, there's this professor called Stuart Wenham, and he's in electrical engineering, but his research is on solar. So he managed to sneak into lectures about diode and about solar cells. So he talked about the IV curve, the current voltage characteristics. He did a demonstration. He took us to the roof and he showed us the solar panel and a water pump, and then a very highly sophisticated advanced cardboard that covers the solar panel. So as soon as he removes the cardboard, the water just keeps pumping. The pump just keeps pumping water, and the only way to stop it is to put the cardboard back. And it was like amazing. I just thought, wow, this is free energy from the sun, and I was hooked. And then I was on a co-op scholarship where I had to work for these different sponsors that sponsor our scholarship, and one of them is Pacific Solar. So it's a startup that was trying to commercialize thin film silicon and try to commercialize crystalline silicon. And it's like funny that, back then they tried so hard to make silicon behave like what perovskite could do, make it really thin, make it crystalline. And because back then the price of silicon was really high, it was like $300 per kilogram, something ridiculous. Because there was a shortage as the manufacturing scale up, and there's a demand and people expand the manufacturing. That phase died, and people worked out how to make silicon in different countries, and they could make in massive amount of volume. and there was no longer any shortage. So there was no case for thin film silicon. But now why perovskite is so interesting is because you can tune the band gap and all sort of other stuff, right? You can make it invisible. You can tune it to such a high band gap that will absorb the UV light and not the visible light. And so, you know, they just open up all these opportunities, and you can solution process it. You can print it. You can print it like a newspaper. So anyway, yeah, that's how I got interested into in solar.
Your dad even made a quip at one stage saying it wouldn't be good to be able to spray solar cells on windows.
Yeah, so he said that, and I went to my supervisor, and he sort of goes, nah, and like not quite sure, you know, silicon's so opaque, why would you do that? And anyway, and then I got funded by Australian Research Council a few years ago working in solar windows. So that was, yeah, I'm really proud of it. I don't tell my parents a lot because, you know, the typical Asian parents, right? I just don't want to set the expectations too high. But sometimes they text me and go, you didn't tell me you won this $2.5 million grant for your, you know, for your projects. Yeah, they always find out from their yum cha friends in restaurants.
I imagine in your area too, clearly communication of your work is important. Why do you think science communication is important?
Yes, because they need to see that there's law and there's order in our world. And being able to understand it actually helps us to work with the environment in the world, to work with what we've got in the world, to appreciate it, and also to make informed decisions about how we live as well, right? So if it's not because of science and the, you know, scientists working on the vaccines, we wouldn't be there'll still be a lot of people dying. And just knowing how the vaccines work, for example, then they will be informed on, you know, how they live, how they carry out their lives, so that they, you know, minimize the impact of, you know, affecting other people or even affecting the well-being of themselves. And same thing with climate and climate change and renewable energy. You know, what is causing the global warming and why, you know, carbon dioxide actually, you know, physics actually absorbs the infrared part of the sunlight really well, and so is water. And that's why our solar spectrum, you know, if you look at the solar spectrum, it's got a big dip in IR on, you know, on Earth. Why? And out in space, it's just, you know, a nice and smooth solar spectrum. And understanding it, understanding the carbon dioxide actually captures the heat within our atmosphere. And then what do we do about it? And, you know, why are we emitting all this carbon dioxide out? And, you know, look at our energy use, you know, in a scientific way. You know, 40% of our energy use actually goes into heating our buildings in winter and then cooling our buildings in summer. How do we design buildings as well? How we use energy efficiently. So all these, I think it's very important that, you know, we are able to think in a scientific way, which is, you know, an informed way of, you know, understanding how things work and therefore make informed decisions, rather than relying on opinions and spin, yeah, and other things that are just more subjective. Although science can be subjective too.
How do you mean?
Sometimes the way we interpret data, sometimes we may have a preconception. Sometimes we may have a hypothesis that we want to prove so badly that, you know, we design our experiments that is not objective enough. We don't include enough controls in our experiments. And also the way we communicate impact as well, and the significance of the results. Some people are very good at it, and sometimes people may not be good at it. And I think we just have to have a very measured way of communicating what we do. You know, give credit to, you know, to the real significance of the work and the real impact of the work.
Let's say you've got a high school student in front of you and says, Anita, what advice would you give me? I'm thinking about doing science in high school, in the upper years, and maybe university. What advice would you give them?
I think get all the fundamentals right, you know, get your mathematics right, make sure you really understand. And if you don't, you know, always ask the questions, ask curly questions, because it's when you ask curly questions that forces you to really understand it. And the other half is, do work hard, do put in the effort, and do try to use what you learn in science and try to apply it in life, and enjoy the projects that you do, and try to see the relationship between the scientific principles and how it is being used. Also, always find ways that you can improve the world, and see if science can contribute to that.
What if the student says, I don't know what to choose, whether I'd agree to go for chemistry or physics?
Wow. Okay, well, which one do you like most? Talk to your science teacher. And if you need help, there's so many resources, right, on the internet. I remember back then when we were at school, and if we couldn't get the answers that we wanted, from maybe, the teacher, we just went out and, get help. And back then it was even harder, right? It was all pen and paper. There was no such thing as the internet. But now the kids can go on to the internet and, see clips like Physics High, those done by yourself and also other people in the world. I think it's a bright future for science students, actually, because they just given so much information. If they're able to harness that, they will just be more advanced than us. They will know more, and they'll be able to solve harder problems because the technology is also advancing, right? Back then, we were not able to look at things in nanoscales. We were not able to do things with such accuracy. But now we're able to do things that we were not able to do that before and 10 years ago. And some of the ideas we were not able to demonstrate or execute, now we're able to. So yes, it's an exciting future for science students.
And in many respects, your work says do both, do chemistry and physics. I mean, your area,
yes.
You're solving a world problem, but you're actually incorporating both your physical skills as well as your chemical skills.
Yes, and I find it increasingly important that big problems need multidisciplinary approach, and you need people who's got different specialties and skills and expertise to work together. So ever since I've joined University of Sydney, I've been working with people from School of Chemistry and Engineering, and even in publications now, people look for both. They look for the science, they want to understand the scientific principles and understand how it works. But they also look for the engineering. So how do you use that to achieve an outcome? So it's increasingly so, it's not just fundamental research, and it's not just engineering. You need the understanding as well.
Now, my final question to you, Anita, is this. What are you nerding about at the moment? So in other words, if you are in mixed company and someone asks you, what are you really excited about? And it doesn't have to be science related. What's the one thing that comes to mind for you?
If I'm not doing science, I cook.
Yeah.
And I always see an analogy between cooking and making solar cells. And there seems to be a pattern between cooking and making solar cells, because I noticed that people in our research group who make very high efficiency cells tend to cook at home. And especially the boys who cook for their wives. And once I had a student, he spent a whole year, he couldn't get a good solar cell out. And I asked him, I said, do you cook at home? He said, no, I don't. So instead of, giving him more solar cell processing recipe, I said, just go home and do, cook me a dish. And he did. So he took photos, he took videos, and, he told me how nice it is. And he could make better solar cell afterwards. And I think, just using a hand. And sometimes with science, there's a bit of intuition as well. Sometimes with science, you've got to use your senses, right? So one example is we used to put dielectric layer onto solar cells, and does a few things, like it pacifies the surface. Surfaces has got lots of defects and dangling bonds, and surfaces are not always finished properly, and they're a bit disorder, and it will contribute losses in the solar cells. So we put dielectric layer to finish off the surface, but it also gives you an optical effect. So quarter wavelength principle, and also you can do double layers. So you're playing with the different refractive index to make sure the light that gets reflected at different interfaces, they will interfere deconstructively and minimize the reflection. So anyway, you can measure. So one way to quantify the thickness of that layer, or that dielectric layer, is to measure it. Or you can actually just use your eyes. And it's amazing how sensitive our humans' eyes are. And we were so good at it that I could just look at the color of the solar cell after the layer deposition, and I can tell you it's 1100 angstrom or it's 200 angstrom. And it follows a sinusoidal relationship as well. So it will go blue, and it goes yellow, it goes purple, and then if you increase the thickness, it will follow that pattern again. And I remember we were visiting a manufacturing plant of solar cells, and we talk about how do you screen the cells in terms of the uniformity of those layers. And I remember the comment was using your naked eye. So our naked eye is a lot more sensitive than machine when it comes to gauging the uniformity of the layer, and that's amazing, right? So our naked eye looking at the TV screen, if it's non-uniform, we can just tell. So you use your sense, you use your sight. Sometimes you even use your smell. So if you're a chemist and something is burning, something on a hot plate is burning, or the smell's not quite right, then you're doing a process wrong, or the pump is failing because it hasn't got the pump oil needs refilling. You need that, and hearing as well. Sometimes you're doing a process in a vacuum chamber and you can hear the pump is not working quite right. So I think it's also intuitive when you do science, because you're interacting with the environment, you're interacting with the process, you're observing, you're looking at data, you're looking at patterns. So it relies on all the human senses and the intuition. And of course, we're looking at machine learning, right? See how machine can actually think like human and recognize patterns. And I think with cooking as well, right? So Asian cooking, they never tell you how much do you put in. They just say, oh, roughly that, a pinch of salt. Well, how big is a pinch of salt, right? So it's all using your senses, using your intuition, using experience. And I think sometimes science is a bit of that, and science needs sometimes a bit of accident as well. People find things because for example, I heard a story between a Korean researcher and Japanese researcher. They're trying to communicate to each other an email in English, and Korean research mistook it, and he makes this material that is like using a solvent that is 100,000 times more than it should. And then he found this new material that contributed to, organic LED. And I think with cooking, sometimes, it's the creativity and the adventure, the experiment. And of course, if you're able to explain it, that is better, right? So anyway, my pastime is cooking.
What's your favorite dish?
Anything to do with chicken. I love using the grills. I love, the ability to do it so that, the temperature is right, the duration is right. And again, it's, hearing the sound, hearing the sizzling, smelling it and knowing when to time it.
Well, it's been a wonderful chat with you, Anita. I've learned a lot myself as I've talked with you. Really enjoyed our conversation. And I do hope you all the success in getting the solar cells to a level where we can make a significant impact in renewable energies. Thank you for your time.
And thank you for having me, Paul.
Well, I hope you enjoyed this episode. Please subscribe to get notifications of up-and-coming interviews as well as my other physics content. My name is Paul from Physics High. Till next time.